Okay. Thank you for coming. So today we're very pleased to have Bruno Camden be the speaker. He's presenting some joint work with Mustafa Perni. And just like to give you some of the highlights of his extensive bio. And so Bruno is a co-founder and principal of Lepton Actuarial and Consulting, which is a New York-based professional firm. He also teaches at George Washington University School of Engineering and Applied Science in the Department of Engineering Management and Systems Engineering. Prior to his current consulting and teaching arrangements, he worked with the Office of Research, Evaluation and Statistics of the Social Security Administration, where he advised the commissioner on mathematical statistical trends regarding medical vocational guidelines and formulated models involving retirement probabilities for multiple years. He's published in quite a few journals, among them Review of Economics and Statistics and Econometrica. And he's worked with many tools common to quants, and he has PhD in Systems Engineering Operations Research from the School of Engineering and Applied Science at George Washington University, as well as an MS and a BS from University of Maryland. Okay, so we're a fairly small group, and Bruno kindly agreed to just take questions. So if you want to ask something, just unmute yourself and ask away. And with that, I give you Bruno Camden.
Yeah, thank you, Professor Clark. It's a privilege to be given this seminar at NYU. So we having a very interesting topic. It's actually a very I would say actual topic, and given the discussion about the cap and trade, the emission, the effects of greenhouse gas emissions. So we're going to talk about that today, and I appreciate your introduction, Professor Cap. It's an honor. So first of all, we look at the conundrum. It's a real conundrum going out here. I think many of us are aware of it, and we will formulate the problem in mathematical terms, and then have a little panoramic view of what we're going to be doing today. And after that, we'll talk a little bit more specifically about some of the things we'll be working on, namely the penalty function, the profit rate function, the payoff functional, and the non-cooperative Nash equilibrium, the long-term lease, and we're going to have a little overview of that, and then the short-term lease, and propose an algorithm for that. So first of all, the problems that's going on, and we know that there's a lot of problems with the greenhouse gas. First of all, as we know, oil production has been skyrocketing in the past few years because of the demand as well. It's been a huge mountain of oil demand, which has provoked a tremendous amount of oil production, particularly in the United States with the discovery of shale and fracking in the past few years. So these are really good opportunity. They're very good, but they created new challenges given the worldwide low carbon energy transition. So what we're going to be doing in this paper, we're going to quite modestly try to construct a strategic cap and trade fiscal protocol under which oil producing government and oil company successfully mitigate CO2 emission. And the total amount of emission permit issued by the government only allow the oil company to extract the oil field at an extraction volume, U1, not to exceed zeta. Zeta here is the cap. So that's what we're going to be doing. That's the conundrum that many policymakers and government found themselves in. So this is the formulation problem. So in this formulation, we look at the oil price, XT, and kappa is the mean reverting coefficient. If you look at this equation here, kappa mu of alpha, where alpha is the Markov change, and mu here is the long run mean of the Markov change, Markov chain. And if you look at this particular expression, that's the mean reverting factor here. or the Austin-Uhlenbeck process. And I think Professor Carr, your Professor Carr has published on that.
It's an OU process for log of oil.
Yeah, OU process.
Right.
Professor Gémen, you guys have what we call in French nobelisables. Vous êtes des nobelisables. So we never know. Just pay attention one day. So this is a very important paper here by Professor Carr, Professor Gémen, and Professor Madame, and happily Professor York died some years ago. And another source of inspiration of this paper is Schwartz and Gibson and Schwartz. So these are some of the main sources of the model that we're using. And here gamma is just a measure of the intensity of the jump and size of the process. Here we're dealing with a Levi process because of the jump in the oil price. Professor Carr paperwork talks about that quite a bit. And N here is the compound Poisson process, right? On a Borel set, you see the Borel set just a subset of the Lebesgue set. This allows us to measure the jump, right? The Levi process, because the oil price here has a Levi behavior, and we need a Levi measure to do that. So that's justify this expression here. And then U1 is the extraction rate of the field, of the oil field, right? Y is the remaining portion of the oil field that need to be extracted. That's a function in time, right? As time changes infinitesimally of that extraction rate. So at the initial state, initially, the value of the oil price is X, and the value of the remaining portion of the field, the oil field, is Y, right? So that's one of the main parameter of the construction of or formulation of the model there. So now a little panorama, so overview of what we're going to be doing. So first of all, we have some admissible control, right? These are the admissible control. U1 lower bound for U1 and upper bound for U1. These are the extraction field, right? These capture the interval in which the oil can be extracted. And this is the tax rate, the lower bound of U2 as well as the upper bound of U2. That's the tax rate. And then we look at the extraction function. The extraction function here is given by CO. That's the initial cost for setting up an extraction. You know, if you look at Shell, BP, they have initial costs, and M is a constant, all positive constant that capture or that control the costs. Actually, if you graph this function, you realize that it's not very far from the cap plus production function. And then you have the emission function, right? The emission function is PU1. We're going to talk about the emission function a bit in a couple of minutes because it's a little tricky. We have to be very careful about that. And then we have the profit rate for operating the mine, which, as you know, is the production function of the revenue minus the cost of operating the mine, and then the emission costs of operating the mine. So, and then we have the profit rate function, the terminal rate function, PR functional, and the value function, as well as the Hamiltonian that we're going to be talking about more in a few minutes. So now we're talking about the emission function. The emission function is defined on an interval. So evidently, this is not continuous here, right? This is a penalty function. It is not continuous. That's why in the paper, we rather use equation number 3, which is continuous, right? Zeta is the cap. Right now in California, they have a cap. I think I was listening to a radio podcast recently where the state of California had put a 335 million metric tons for cap, right, as a cap of new greenhouse gas emission. And if the extraction rate is less than the cap, what happens is that the company is given permits, right? Is given one permit per emission ton of carbon the state want to emit. So if they're less than the cap, then they can go and trade the permits, right? They can go and trade. There's a whole market now, auction, where people, oil company can trade the permits, the carbon permits whenever they're not exceeding the cap. However, if they exceed the cap, they penalize, right? They penalize, and they also have incentive. Pardon me. Here, psi is an incentive parameter, right? To kind of push this company to go and work on the in a way that the extraction rate will be less than the cap. So that's the penalty function there, or the emission function. So we use this here because it is continuous. Now,
yeah, but also let me comment that not only is 2 discontinuous, it's not concave either, right? It's there's like a, I mean, well, so
yeah,
yeah, I mean, 3 is advantageous because it's both continuous and concave.
yes,
Yeah, okay.
that's correct. Thank you.
Yeah.
Correct. Yeah. So now let's talk about the profit rate function. This is important because a priori, if you look at this equation here, a priori, if you don't have U2 here, you don't have the tax rate here, a priori. But if you look at it, that's what we call a posteriori, the tax rate occur. So here we have the total profit rate of operating the mine, which is evidently depend on the extraction rate of for the mine. And then you have the oil company pre-tax profit rate, which is theta times P. Theta is the share or the portion that need to be the portion of benefits. So if the company get theta, the government is going to get 1 minus theta. And that's why the government profit rate function without the tax revenue is 6. Now, if you look at the total income tax, the government levy on the oil company, that's 7, right? So you have the tax rate, right? And theta. So ultimately, you realize that the government profit rate function depend on U1 right here. So it depends on U1. And that's what we have here in equation number 9, right? So that's the problem there. So that's the setup. Now we look at the payout functional. The payout functional is just like awards. So you have the payout functional for the oil company and the payout functional of the firm, which is R1 is just the post-tax profit rate function of the oil company, as well. L2 is the government profit rate function of the oil company. So that helps us to find the functional, right, which is pretty well known function. Whereas phi 1 and phi 2 are the terminal profit rate function. So phi 1 is the terminal profit rate function of the oil company, and phi 2 is the terminal profit rate function of the government. Now we look at the Nash equilibrium. Now we want to find a non-cooperative Nash equilibrium such that the payout functional of the oil firm is greater than the payout functional of the uh, of the R firm, but a different, right, at the optimal tax rate, right? Given the optimal tax rate of the government, the PR functional of the oil firm here has to be greater than the PR function of the oil firm there. So that's why it's a non-cooperative national equilibrium. They know the equilibrium, but they don't know exactly what each one is really doing there. They don't really have, it's not part of the game of the preamble of the game. Now, if you look at the PR functional for the oil company, and you look at the optimal. No, that's a fair, this is the PS functional for the government. The optimal extraction rate for the oil firm. So here the oil firm look at the optimal extraction rate of a tax rate, and here G2, that's the government, look at the optimal extraction rate of the oil firm. So this here has to be greater than this one here. So we define the Nash equilibrium as for differential game as the value function, right? Which are the maximum, the supremum of the pair functional for player one, and the supremum of the pair functional for player number two. That's the government. Player one is the company, and player two is the government. Now we have the Hamiltonian, right? The Hamiltonian help us to eventually get to the Hamilton Jacobi-Isaac equation. So the Hamiltonian here is what is, if you look at some discounted rate times the value function of each of the players. So here it should be V1, but it really doesn't matter. So these are the Hamiltonian. So you see they depend on the value function and our initial problem. We have kappa, we have mu, and for each Markov state. This is for player number one. So here the Q is the generator of the Markov change, right? The derivative of the original Markov change. I think this is not all the new variable. And then we do the same thing for player number two. So once we have the Hamiltonian for player one and Hamiltonian for player number two, then we're ready to go and get the Hamilton-Jacobi-Isaac equation, right? So we just have to derive the Hamiltonian, the respective partial derivative, and then we get the Hamilton-Jacobi-Isaac equation, and our result would depend on this, as we state in the next slide. So here, first we look at the long-term lease, right? Lease T greater or equal to 30 years. In some, I think it's quite often in, you can find it here in America, where some oil firm can sign lease for more than 30 years. It's more, it happened more in Africa, in African country, where you have an oil firm that sign lease for over 50, 60 years. In Cameroon, my country, for instance, they have I think they have a contract for 100 years. So that's the first case of the application of the Nash equilibrium. So assume that there exists a Nash equilibrium U star one and U star two. The solution of the Hamilton-Jacobi-Isaac equation are V1 and V2. Okay.
Bruno, I just have a clarifying question. Mm-hmm. What is the economic or financial meaning of the second argument of the value functions denoted by I?
Okay, so
time or what? Yeah, I've lost track of it.
It's the Markov chain. The Markov chain.
Oh, it's a Markov chain. So it's the state.
Yes, it's state.
Okay, fine.
Yeah.
Okay.
Yeah. So that's the state of the Markov chain.
Okay.
Yeah. So this theorem is this theorem, to prove it, you have to derive kx. Right? We have the proof in the paper, but the most important part of the proof is kx. And we call it the cap trade contingency factor for maximum oil impact strategy. For optimal, I would say, optimal stats, oil instances, or oil impact strategy. The interesting thing here is that kx, which is our contingency factor, actually depend on a few things that we started with. First, zeta, right? The incentive. Zeta. Remember, we talked about the incentive. This incentive is very important. You go in California, for instance, very, very important in helping in getting a company to produce under the cap, to reduce the greenhouse gas emission or CO2 emission. Very important. So that's the contention factor there. That we get it as we prove this theorem. And an X tilt is a factor that helps us to see things very clearly, Evan. So here with X tilt, you have C to the initial cost of extracting the firm. You have zeta, which is the cap. You have psi, which is the incentive. And you have M, which is the control parameter of the cost function in extracting or the oil firm construction or cost function. So, and here, so if you want to look at it more closely, because this is a closed solution, here we get a closed solution, in contrast to short-term leads. So you have your value function, each state, and then you have the coefficient A1i and B1i for different state. I think we found a case of a two-state Markov change. We don't have the data right now, but we're looking at the data. And then you derive the optimal extraction rate, right? The optimal extraction rate is
inverse in the price.
yeah. U1 star, which depend on one of the parameters in the cost function of a producer firm, and what the incentive psi, right, over x. X is the initial value of the market price, of the market's the price of oil. And then you have k and x bar. So what happened if kx, right? Remember, we already have an optimal rate, rate for the extraction rate. Now we need to look at the optimal tax rate. Okay, so when kx is less than 0, if that.
I've got a quick question.
Yeah.
So back to U star 1, the right-hand side, which is m plus psi over x, doesn't seem to depend on I. Am I right about that?
U star 1.
Yeah.
Yeah, that's correct. That's a good observation, Professor Carr. Yes, that's correct. Yeah. So yes, yeah, that's a very good observation.
So let's say so the state I is not affecting the optimal extraction rate, apparently.
Yes, the state I is not affecting the optimal extraction rate. That's I think that's a very good finding there. Yeah. Thank you. And then
so, yeah, I must have missed the Markov chain part, but what is it that's following a Markov chain?
Okay, here. Right here. So this is the Markov chain here.
So alpha there. So alpha is following a Markov chain.
And alpha S, the initial state is alpha S. I think I will show put it here. The initial age state of the Markov chain is I, right?
Yeah.
Yeah.
So the mu there is like some long run value for oil.
Yes. Mean, yeah.
And okay, and I guess the square brackets mean is a function of. So you're saying the long run value of oil is a function of a quantity alpha following a finite state Markov chain. Is
Yes.
that right?
Yes.
Okay. Okay.
Correct.
Is there any reason actually to make mu a function of a Markov state Markov chain as opposed to just saying the long run mean is a finite state Markov chain? Is there it just so I see alpha appears also in the gamma, so I guess that's why you did it that way.
Yeah,
Okay.
gamma is the jump, right? So
Yeah.
gamma capture is capture the jump
Mhm.
in the oil price.
It also affects sigma. Okay, I see.
Yeah, so that's why we have
So,
Levi.
okay, so let's say all the coefficients are
All of the
changing state simultaneously as the Markovs as alpha transitions from one state to another. Okay.
Yeah.
Okay. All right. Now it's become clear. So, okay. So the conclusion though is that the optimal extraction rate, which is in the second equation here, I mean, well, okay. So U1 star anyway.
Okay.
Doesn't depend on which of this.
Yeah, it doesn't depend on that state there. So that's it doesn't depend on that state. I think it's a good observation. Now, if K, which we call earlier, or carbon-free contingency factor, if K is less or equal, if not, or greater than 0, in which case X is greater than X tilde, then the optimal tax rate is just the lower bound of the tax rate, right? But if Kx is greater, if it is less, okay, so if Kx less or equal to 0, if that's not true, then the optimal tax rate is the upper bound of U. And if it is true, then the optimal tax rate is the lower bound of the tax rate. Just remember that we define our tax rate and our extraction rate here as upper bound and lower bound, right? So, and did not 0 at all. Okay, so now let's look at the short-term lease. This is a case very frequent case. You go to different states, Texas, you have a lot of oil companies that have short-term lease, less than 3, 4, 5 years, or less than 30 years, a few years. So in this case, if you look at the value function VI of the non-cooperative GAM, these value functions are respectively unique viscosity solution of the Isaac equation 16. Okay. The proof of this, the elements, the most important element in the proof of this theorem can be found in the following 2 books: Applied Stochastic Control by Bernd Oxendorf and Sulem, and the other book is Fleming. It's a standard classic book in optimal control. So that's where the proof of this theorem. So the element of proving this theorem can be found. They mostly based on the Lipschitz continuity of V1 and V2, and then we apply the principal dynamical system, and then we can come to that solution. All the elements are in the paper. So now, so unhappily, this case for short-term lease, we don't have a closed form solution, so we have to we have to use iteration difference method to find the solution. So what happened is initially you have a
let me just stop you a sec. So is the reason you do have a solution when you have long-term leases is the reason that let's say time stops being a state variable? Is that why?
Yeah, as time switching, that T goes to infinite. Yeah. So yeah.
Okay. So it's kind of like, for example, with American put options. There's been a solution since the 60s for a perpetual American put option, but to this day, there's no simple solution for a finite lived
Yes,
put option. Okay, so it's like that intuition.
that's very, very good analogy.
Okay.
So here we really don't have a closed form solution. We just have to go through this difference method and using this algorithm. So you assume you have a tolerance. The tolerance level is epsilon. If is greater than 0, then you choose an initial guess for the value function, and for the iteration from for j from 0 to maximum iteration, you find the optimal strategy u1 star and u2 star. In which case u1 star is the argument of the maximum of u1 partial of u1 respect to yn plus the profit rate function, and then u2 as well. And then you set the value function at the next state is equal to 1 over r. Here, delta s is the finite difference operator for the initial state. You set that in plus 1 over r. R is the discount rate times the partial of the Hamiltonian was u1 star and u2 star times the value function at iteration j. Okay, if the norm Vj plus 1 minus Vj is less than the tolerance, then stop. Otherwise, you move to the next iteration. Okay, that's pretty much the algorithm for this. Right now we are working on the data. We have a solution. We test them on MATLAB and the closed form as well as the non-closed form solution. So we're looking at data. I think some encouraging news we have recently is that in the state of California, as we discussed earlier, they're really enforcing the cap and trade regulation, and many companies are getting into it, as we discussed earlier. So this paper has twofold. Two researchers. Through this paper, we offer a multi-valent and strategic model that can be computed in closed form and into policy and in non-closed form as well. And to policymakers, we resolve a very important policy conundrum by proposing a fiscal toolkit that, on the one hand, mitigates CO2 emission through an efficient cap and trade system. We talked about the cap and trade contingency factor. On the other hand, our proposed fiscal toolkit maximize revenue for the government entity and return for the oil company. So we sort out the complexity related to the global greenhouse gas transition, and I think this is going to be very, very important for the future as we move forward with fire in California. I think it's brought quite a bit of awareness of the need to really control for CO2 emission, and this paper really helps sort out the complexity related to that. We really are looking and initially a very strategic cap and trade fiscal approach that will serve as a template for future research on the mitigation of CO2 emission using optimal control. So, and the other thing we do in this paper, which is not very popular right now, I think we'll probably be some of the few to do that, is that we take into account the random dynamic of the oil price by expressing it as a mean reverting region, switching the Jones diffusion Levi process, and obtain an optimal production path that is successfully integrated into this.
Just want to make the comment that it feels like the problem you solved is even more useful than you're suggesting, because although you pitched it in the context of oil, I didn't really see why we had to make X be the oil price. It could be the price of anything that one is extracting, which, let's say, some somehow, like what, you, but it
Gas,
would limit the
gas.
extraction. Like if it was fishing, for example,
Mhm.
if we want to prevent overfishing just as much as we want to prevent taking out too much oil out of the ground. I mean, it's the same math, right? Is that fair?
Something that's true. That's true.
Okay.
Even the coal, we can apply it to coal.
Yeah.
You can't be correct. Yeah.
Yeah. So, okay, yeah, so that's quite impressive. Actually, I was kind of fascinated by the fact that your optimal U1 star was independent of the Markov chain in the long run setting, long run lease.
Yeah.
So is the optimal tax rate also independent?
Yeah, I think it is. The optimal tax rate here. Okay, I think that.
Oh yeah, so that's over there.
Yeah.
At the bottom. So yeah, okay. So what is U bar 2 again?
Okay, U bar 2 is the upper bound of the
upper bound, right?
Of the tax.
Yeah. Well, that will be independent of the Markov chain.
Yeah.
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 Okay. So you're also saying, right? So you're saying with the tax rate, are you saying that the only two solutions are bang bang, go as high as possible or go as low as possible?
Yes, that's correct.
Okay.
Yeah. So yeah, that's correct. I think my co-author is here. He can chip in. I think I saw him sign in. So what's happening? We found the optimal extraction rate, and then, but that's not all. We need to find this parameter K and X tilde. So K and X tilde are very, very important parameter. Both of them depend. We better work with X tilde. In the proof, along the proof of this theorem, we can derive X tilde and that's Kx. So you see, X tilde is pretty straightforward. If you have the problem with Kx is that it depends on X. But if you have X tilde, if you have the initial cost of operating the oil firm, if you have the incentive, right? That we can have it. If you have the cap, zeta, we just spoke about the cap in California right now being $233 million tons per carbon dioxide emitted for the whole year. So it doesn't have to go that far. So, and then we have the M, which is a parameter factor in the cost function of the oil companies. We can have this. That's why it's good to work with. It might be a little easier to work with X tilde. So if X, the current price of the oil is less or equal than X tilde, then the optimal tax rate will be the lower one, right?
Okay.
But if it is not less or equal to X tilde, then the optimal tax rate will be the upper bound, right? And usually the upper bound and lower bound that define the contract. When the government signs a contract with the oil company, this is how much you can go. The oil company and the government say, okay, this is the maximum tax I can pay, and this is the minimum tax I can pay. Yeah, sorry.
Yeah. So it's an implication of the model is if oil prices go from below X tilde to above, the tax rate's going to go up too.
Yeah.
And so, I guess the intuition is higher oil prices mean richer oil firms, and so you tax them more.
Yeah, that's correct.
Okay.
Yeah. And then I think my co-author is here. He can talk. He can. I think I see him. I don't know. I think he's here. I think somebody is asking a question.
Yeah, feel free, anybody.
I guess the blue hand is mine.
Go ahead, Tony. Yeah.
This is really fascinating because I've had to deal with similar problems with NOx and SOx credits for running power plants, and they expire.
Battery 55%.
Oh God, I can't believe that's happening.
55%.
Yeah.
Sorry about that.
55%.
Okay, I'm
Are
on a
you?
boat and I'm doing this on a cell phone, and it's
Okay.
telling me that I'm halfway out of juice. Anyway, um, the if I understand this correctly, it's a long run mean. The Markov process is a long run mean for the forward price of oil.
He didn't deal with forward prices, right? You were just dealing with spot prices,
Yeah,
right?
yeah. I'm just
Right.
looking
But
at
but
the
there is a forward price of oil and a forward price of the pollution credits.
Okay.
Is it possible to sort of have the Markov price grow, okay, at something approximating the forward price of the oil and the forward price of the pollution credits?
Okay. Yeah, I think that will depend on whether um, this condition is met. Uh, uh, this condition here. Okay, if the extraction rate is less than uh, the cap and trade zeta, then the company is going to have pollution credit. So they can go into the market and trade the permit, the credits, the credits, and it's happening right now at auction. A lot of companies are making money out of that. As long as they don't pollute too much, the government is going to give them permits, and they can trade it and make money. So in that case, then you can have a forward price of the pollution credit.
Yeah. So in equation 3, which is the one the penalty function you ended up using here, I guess I mean, financially it's saying if U1 is above zeta, then there's a penalty. But if U1 is below zeta, then instead there's a reward, right?
Yes, right.
Yeah.
That's excellent, Popsicle. Yeah. So if you look at it, if U1 is above zeta, the log of U1 over zeta is positive, right?
Mhm.
Right. It's positive. So it's actually a reward function too.
Yeah.
But if U1 is
You earn money by
less,
not extracting oil.
yeah,
Some, right?
U1 is less than zeta,
Yeah.
U1 over zeta is going to be negative. So in that sense, yes. And this is
Yeah.
actually a
So like, so if I mean, like say this coefficient, I think it's pronounced xi, the thing that looks, the thing in front of log. I think, so say it was huge. I mean, just thought experiment. And so say it was nearing infinity, then, well, everything else stays finite. Then it's an incentive, like basically oil firms are incented to not produce, right? To not extract,
yes.
right? At all, like they should.
Yeah.
I mean, but actually, and this raises something else I was thinking about. So, okay, so they would lower their U1. With psi was huge. They would lower their U1, you would think. But let's say the lowest, are you enforcing that the lowest U1 is 0, or does the math allow U1 to be negative?
Yeah. We're enforcing that the U1 is less than zeta. So as long as you
U1 is greater than 0, right?
Yeah.
U1 is the extraction rate, and the math is not allowing negative extraction, which is which makes no sense physically, but math doesn't know about physics clearly. So okay, so anyway, you made the math problem such that U1 was always greater than equal 0, right?
Yeah.
Okay.
Yeah, that's correct.
Okay.
And right now in the state of California, I think in the state of California, the cap is at 335 million metric tons of new carbon emission. And in California, it's $70 to emit 1 ton of CO2. So if you want to emit 1 ton of CO2, you're gonna have to spend $70 in California right now. So if you can multiply that by 335 million, I think you should get quite a bit of money there. You can understand that many oil company are really making money out of this cap and trade policy. But as long as they
Yeah.
emit, uh,
Yeah, could we go back to the optimal solution for that you got in closed form in the long run lease problem?
yeah, for the
Yeah.
this.
Yeah, here exactly. So, yeah, I'm focused on you 1 star yet again.
Yeah.
And I've just I understand that the division by X is the division by the spot price of oil.
Yeah.
Now the numerator, I actually lost track of what everything stood for. So
Okay, M is a parameter in the operating costs of the oil firm. So M here is right here. If you let me see whether I think you can see M in the second.
Oh yeah, I see it in the second one. So it's
So
something
that's
to do
the
with
extraction function.
the cost, right?
cost,
So M is a
yeah.
positive quantity
Yes, a positive quantity.
that
Yeah.
that
So here,
says the more you extract, the more costs you have.
yeah, the more costs. Yeah, that's correct. So here we're saying that the optimal extraction rate is
Mhm.
Equal to that parameter in the cost function plus the incentive parameter
Yeah, which we were just.
divided by the market price of the oil at the initial state.
So let's see if I get that makes sense. So actually, like, it's counterintuitive, I'd say, with the incentive parameter, right? Because as we're raising psi, this third, rectangle from the top is saying as we're raising psi, the optimal extraction rate goes up, right? Because X is positive, of course.
Mm-hmm.
And so, but psi was like
Incentive.
was penalizing firms for producing too much, right? That's how it ended up using. So it's
No, psi is an incentive. So it will make
incentive to do what?
If the incentive is more, then the extraction rate is going to be more, right? But as long as it is the optimal extraction rate, we're talking about the optimal extraction rate is more.
Mm-hmm.
But as long as U1 is less than the cap, so as long as U1 is less than zeta, because
Okay.
Because this is, you remember that if U1 is greater than zeta, no, if U1 is less than zeta, is zero, right? Is zero. And so.
So wait, I misunderstood. Are you using 3 to come up with the optimal solution, or are you using 2?
We're using 3.
Yeah, so I thought.
Yeah.
So, okay, so let's talk about 3.
Okay, yes.
So, so in 3, with 3 operating, like I read it as, okay, so first is the row hat on the left is a penalty, right? It's a penalty.
Yes, psi is a penalty. No, sorry. No, psi is an incentive.
Yeah, I know, but the p hat on the left hand side.
The
p hat is a
p hat is it's some kind of penalty function.
Yeah. So forgetting about the right hand side of 3, the bigger is p hat, the worse the firm is, right?
Yeah.
Okay. So psi is a positive parameter, and the bigger is U1, the bigger is the penalty.
Mm-hmm.
So it seems funny to me. Well, I mean, it might be right. It's just not obvious that, so let's say the other result that we were looking at before said if psi goes up, the optimal extraction rate goes up.
Mm-hmm.
That's what it says.
Mm-hmm.
That one is saying, right? If psi goes up, holding everything else constant, of course,
mm-hmm.
then U star 1 goes up. That's what the math says.
Mm-hmm.
So I'm just trying to get, I'm trying to reconcile that we raise the penalty, the parameter, you call it the incentive, that's fine. We raise the incentive to produce less. And it seems that this third equation is they produce more. Isn't that what that says?
Yeah. 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 I think that's that would make sense.
That does make sense.
Yeah. If you raise the incentive, then your optimal extraction, then you're more likely to get the optimal, or your optimal extraction rate goes up if you raise the penalty. Yeah, I think I see the counterintuitive part of it.
Yeah.
Like, you
Okay.
raise the incentives, you
Yeah, but it might be right. I mean, I'm only focused on the simplest, interpretation of things, let's say. So there can be subtle, in economics and optimization, there can be subtle second order effects or something, but anyway.
And yeah, I think Tony has something to say.
Oh no, you lost me, and I'm scared that my phone is going to yell at me again. So I've got nothing to say.
I have a couple questions, if you don't mind.
Go ahead, David.
I'm kind of an energy risk management consultant in one of my former lives. And it seems to me that in my work with producers that they never looked at the production rate as being something that was that controllable, in these kind of land leases, that they basically the size of the pipe determines the rate of the flow, and there's not much you can really do to adjust your production over time once the field has already been developed. Is that your impression, or am I thinking about a small subset of the available oil production sites, or what is your feeling about the realistic nature of that assumption?
Yeah, I think you're making a point, and remember that the production ultimately is a function of the extraction rate. Remember, if like recently in Saudi Arabia, if you remember last year, I think said there was some oil field, some wells that were bombed last year, and then suddenly oil price went up as a result of that. So finally, if you look at it really carefully, everything is function of what happened in the oil field, the oil wells, right? So everything really is function of those extraction rate. It drives everything.
I don't think they have a lot of flexibility on the extraction rate.
Yeah, but David, okay, so that may well be true, but then you just interpret what he's doing as before you build the oil field, how wide should the pipe be, right?
Yeah.
Right. And then of course the counter to that is you don't know ahead of time how much oil is actually there. You have estimates of proven and probable reserves, but you put down the pipe, and sometimes you regret that your pipe isn't wide enough, or it is too wide. So there's not a complete certainty, which is he's assuming here he knows what the reserves are, which is not also not a definite given, right?
Yeah, that's
stochastic parameter. Yeah, that's true. It's not.
Yeah, I wanted to ask about reserves actually. So, so that's the Y variable in your setup. Yeah. So Y starts positive. That makes sense, and you're treating Y as a known amount, as David just observed. And then anyway, you draw it down. I mean, does the math actually stop you when Y hits 0, or does the math let you keep going, drawing down through negative values of the reserve?
No, they might continue. I think the Y disappear. Okay, in this case, for the long-term lease, okay, we have our Y here. Our Y is mainly driven by the extraction rate.
Right. And so I start with like 10,000 barrels of oil known there. And then time goes by and I extract 10,000 barrels of oil. And now there's 0 left. And now is the math going to say you must set the optimal extraction rate to 0 because there's nothing left?
Yeah. Yeah.
It will do that. Okay.
Yeah, that's closing the firm. So when that happens, the firm it moves
okay.
out.
Okay, fine. So
like in some country in Africa,
yeah.
Out.
Yeah. So David's making a very interesting point, which is, I mean, you have a sophisticated model as it is, but it could be even more sophisticated by introducing uncertainty in what the initial level of Y is his point. And,
Can I ask another question as well, if I may?
yeah, go ahead.
So the other impression I have is that while certainly the production of oil causes some pollution, that most of the pollution from oil comes from the burning of oil, not from the production of oil. And I'm wondering if you've thought about the sort of externalities that are outside the system here, because the government's getting a benefit from reduction of pollution from the oil that's not being produced in this scheme, right? But it isn't having a feedback effect on the company itself, except through bearing the cost of cutting its production. You see what I
Yeah.
mean? There's an externality
I
here.
think I may have an insight there.
Okay.
This is Tony again, I'm sorry. Those CO2 credits are interchangeable or have an equivalent trade to natural gas credits, so to speak. And the main CO2 deficit that you get from lifting oil out of the ground is not in fact CO2, it's the release of methane. And methane is about 30 times, the ratio of CO2 to methane is about 30 to 1. So
Okay.
The eventual burning of the oil is taken care of, say, at the power plant level, because the power plant gets CO2 credits to burn the oil. So you're only required to have enough permits for the thing that you do, not the eventual use of the product.
I see. Okay.
So there's more CO2 credits down the line for the burning part. And the guy who's lifting the oil out of the ground is really using the CO2 credits to offset his methane penalty at a 30 to 1 ratio.
But the other effects, if this affects the oil price, if this is done en masse in the US and the oil price goes up as a result, you're also going to penalize the producers in a way as well by raising the price of their output. So people might,
Well,
conserve more or something like that. So I guess what I'm trying to say is that, is there any benefit to looking at this as more like an integrated system rather than, one part of the chain?
I think it would be better to view it as one part of the chain, because no matter what, and given what Tony just said too, you're always gonna have to extract. In order to have oil, you need to extract somewhere. You need to extract the oil somewhere, right? And it takes a lot of toll on the environment when you extract oil, and putting a cap on that will help not only the environment, but also with the trades and permits, it can help the government who are responsible of regulation and help the company who want to make money.
Okay, and one final question, if you don't mind. Is there any feedback between, let's say the government did this en masse and was effective in reducing oil production, arguably prices would go up. Is there any feedback into X in the model for that?
Yeah, actually, the Markov chain captured that a little bit. We have a area when you have a case when the oil price goes up and go down, bill and beer market. Bill, I think B-U-R-L, B-U-L-L, the bill. I can pronounce that well in English, but it's bill market and beer market. So you can see that here. That's why everything is very function of the Markov chain. Everything is function of that. You have mu of alpha t. Alpha is the Markov chain, and the initial state is I. The volatility is a function of the Markov chain. Even the intensity of the jump in the oil price, they're all function of the Markov chain. So when the price go up, all of these parameters are affected.
Okay, thank you very much for your answers.
Thank you.
Yeah. All right. Yeah. Thank you, Bruno. All right. It was very thought-provoking. Okay. Well, that brings us to the end of today's seminar. Just mention that the speaker next week is me, and the title is Simple Bermudan Option Valuation. And look forward to seeing you next week.
Thank you. I'm sure to signing from time to time. So, Professor Carr, I understand that the ECM has been canceled for this year, the Eastern Conference on Mathematical Finance.
Oh, I'm not aware. I just don't know. I haven't heard anything about it, so probably. But I'm not an organizer this year, so
Yeah,
I don't know.
yeah.
Let's see. I'm trying to think what conferences there are going on. So there's Quant Finance Conference coming up in November, early November. It's an industry conference, and Quant Minds International, which is yet a different thing, is around the same time. Okay. So thank you all for coming. Let's stop the recording, Misha, and we'll see you next week.